So let's look at another force and stress application example. So here's our context. So 6 concrete support columns are used to support the floor above in an office building. If each of the columns have cross sections with an area of 0.09 meters squared, what is the maximum downward force they can support together? What is the maximum mass they can support together? So we're going after the idea of maximum. So we really need to think about what we were talking about before, like when is it actually safe for that maximum ability before it breaks, basically. So let's start with sort of visualizing what's happening again. So we have 6 concrete support columns are used to support the floor above. So basically we're just sort of visualizing the idea that we have a floor and we're being supported by 6 concrete columns. So however you sort of draw them, so we can have probably a floor sense, we'll do 3 on each side. So we're supporting this by 6 concrete columns. Basically what's happening. So we want to support that, and each of the columns has an area of 0.09 meters squared. So we know that we have a force coming down, we have a weight, depending on what the mass of the floor is, and then counter that we have 6 forces of the columns coming up, and we know that that's a compressive force that's actually happening there. So if you think about it sort of again in that sort of free body diagram, we have the weight coming down, and we actually have 6. 1, 2, 3, 4, 5, 6 of our columns supporting that particular weight. So each of these is a compressive force that we have that we can sort of balance the two out. So we know we have an area, but they're not actually giving us really anything else in the question in terms of values. So the question is, well, how do we come up with that downward force? How do we come up with that mass that they can support together? So if we think about knowing that we want to support this weight, remember back our weight formula is mass times gravity. But unfortunately we don't have a mass to plug into this particular formula. But we do know what our gravity is, so if we knew what mass is, we could certainly plug that into our formula. So we have to take a different direction. Something to notice is that we actually have area, so that's where we can sort of think about stress coming into play. So remember, stress, in this case compressive stress, is equal to the force, in this case would be the weight, divided by our area. So we have area, but we don't have force, we don't have stress. So we have to sort of think of it in a different way. But we do know what product we're using. So we know that we're using concrete supports in this case. So we did talk about the idea of products and their safety values associated with it. So at the bottom of our page, we can see the different values. So for compressive strength, concrete, we can go to a maximum of 30 megapascals. So that would be actually our stress value, our maximum stress value that we could use in this case would be 30 megapascals. So unfortunately, remember that stress in this formula should be newtons over meter squared, whereas megapascals is not quite in the unit format. So let's start with that to begin with. So we have compressive strength, maximum that it should be is 30 megapascals. We know that the formula gives us actually pascals, so we'll do a conversion on that. So multiply by 1,000,000. So we end up getting 30 million pascals of stress. And then we know what our stress is, we know what our area is, so we can actually find force in this case. So our sort of adjusted formula that is that force is equal to compressive strength multiplied by your area. So we can take the 30,000, sorry, not 30,000, 30 million pascals, multiply it by our area, 0.09, and we end up getting, in that case, 2,700,000 newtons. So I'm going to bring that down here. So we have a force in each of our columns. So we looked at one stress and we looked at one area. So force in each of our columns is equal to 2,700,000 pascals. But we know that the total is going to be supported at 6 times. So let's multiply that by 6. So we end up with a total force of 16,200,000 newtons. Sorry, my unit here should be newtons, not pascals. So now we know what our total force would be. So the total force that these columns can support potentially will be 16,200,000 newtons. So that's part of the question done. So the maximum downward force they can support is, like we said, 16,200,000 newtons. The maximum mass they can support is using that situation. So that would be like our weight. So that's our maximum weight that we can use. We know what gravity is, so we can actually use this formula in an altered way to find out what our maximum mass would be. So using this formula, mass would be weight or force divided by gravity. So our weight, maximum weight that we can have is 16,200,000. That's in newtons divided by gravity, which is in 9.81 meters per second squared. And when you do that division, you end up getting mass coming out. And I ended up getting, please check with me on the calculator, 1,651,376.15 to 2 decimal places, and that would be your mass in kilograms. So our maximum weight of the floor will be the following. So, sorry, not maximum weight, maximum mass. And our maximum weight or maximum force would be the 16,200,000 newtons. So this is our maximum force. Or you can think about it as maximum weight that it can withstand. So it's important to make sure that if you are given sort of actual material, that you can use that information to solve other values that you care about in your formulas.